This is ARTiS, the Automated Reformer Tube Inspection System, developed by TCR Advanced Engineering and TCR Engineering Services of India. Over the next 20 minutes, we will work through four things. What actually ends the life of a reformer tube? Why creep damage stays invisible to a surface method until most of that life is gone? Why ARTiS reads the damage with ultrasonics rather than eddy current, which is the question we are asked most often. And how four measurements taken by one crawler become a retirement date for every tube in your furnace. An inspection that tells you a tube is damaged has answered the easy question. Every method on the market can do that much. The question that actually governs your shutdown is different, and it has three parts. Which tubes come out at this turnaround? Which ones will survive to the next one? And what the reformer is safe to run at until then. ARTiS is built around that second question. It is a condition assessment, a fitness for service evaluation, and a remaining life assessment carried out to API 5791 and ASME FFS-1, and it ends in a date, not an adjective. Primary reformer tubes hang in the radiant box of a top-fired furnace. Tube lengths run to about 15 meters, and the working condition is around 900 degrees Celsius at 25 to 30 bar. Two consequences follow from that geometry. First, manual ultrasonic scanning of those tubes means building scaffolding, and scaffolding is the reason inspection scope gets cut when a turnaround runs late. Second, whatever you inspect from the outside while the damage develops on the inside. ARTiS is a crawler. It clamps onto the tube at platform level and climbs the tube it is inspecting. Hold four numbers in mind for the rest of this session. A reformer tube is designed for 100,000 hours, about 11 and a half years. Plants that operate inside the envelope and inspect on a cycle have run the same tubes past 200,000 hours, about 23 years. An overshoot of only 10 to 20 degrees Celsius in tube metal temperature roughly halves tube life. And ARTiS sets the retirement date at a life fraction of 0.8. Rising throughput shortens reaction time and pushes furnace temperature up, which is why tube inspection now dominates the turnaround. The gap between 11 years and 23 years on identical tubes is operational control, and it is worth more than any alloy upgrade. Four things drive it. Every tube runs at the edge of its creep limit, so minor process variation matters. The tube metal temperature you measure is not reliable because pyrometers work on emissivity. A new rough tube reads near 0.9 and oxidation drives it towards 0.6. Catalyst condition moves the temperature, a changeover alone giving 8 to 10 degrees. And startup and shutdown transients are where accumulated damage peaks. 6 mechanisms act on a reformer tube, and they do not respond to the same measurement. Creep damage, metallurgical degradation, where carbides coarsen and creep rupture, strength falls without any crack being present. Localized overheating and thermal shock, external oxidation, which the field calls baldness, bowing and wedging, and catalyst deterioration, which channels the gas path and raises local temperature. Notice the trap in the fourth one. Oxidation removes wall from the outside, while creep adds diameter from within. So a diameter reading on its own can underreport creep strain. Creep damage does not start at the surface. It starts at mid-wall, where hoop stress and thermal stress combine. Isolated voids appear first, at around 40% of consumed life. They align at around 55%. Aligned voids link into mid-wall fissures. Only in the final stage does cracking reach the outer wall at 75% and beyond. Follow that sequence carefully because it settles the technique question. A method that can only interrogate the surface is waiting for the last quarter of tube life before it has anything to report. Here's the answer to the question we are asked most often. Put the two techniques on a life consumed axis. Transmit receive ultrasonics interrogates the full wall thickness, so it responds to carbide coarsening and to the first isolated voids at mid wall from roughly 40% of consumed life onward. Eddy current is a surface and near surface technique. Work reported to NACE finds it unreliable for damage below about 30% through wall, which on a reformer tube means it becomes dependable only once cracking has worked out towards the outer diameter, around 75% of life. 4 reasons, stated plainly. Depth. Ultrasound penetrates the full wall of a thick cast tube, while eddy current penetration falls as conductivity and permeability shift in service. Creep quantification. Attenuation in decibels tracks microstructural degradation, which gives a graded reading rather than a yes or no. Inner and outer diameter flaws. Ultrasound sees cracking from either surface before it breaks out. And pairing. The same crawler, pass that logs attenuation, also logs outer diameter and bowing, and those three feed one remaining life model. Eddy current supplies none of them. Here is the physics. ARTiS runs ultrasonic inspection in transmit-receive mode. Energy enters the wall at one probe, travels through the mid-wall and is received at the other. What arrives is what was sent, minus what scattered on the way. In as-cast metal, the beam scatters at dendrite boundaries and primary carbides, and that scatter is your baseline. With surface exposure, secondary carbide precipitation adds to it. With creep, voids add more. Once voids align into mid-wall fissures, through transmission is largely blocked and attenuation rises sharply. The decibel value is a direct measure of energy lost inside the wall. A number on its own is not a judgment. TCR reads attenuation against a reformer tube reference space. 35 to 55 decibels corresponds to as-cast metal with dendritic columnar austenite. 55 to 62 indicates aged material where the eutectic carbide morphology has changed. 62 to 72 corresponds to 80 to 95% of life consumed, with coarsened carbides and interdendritic microfissures. Attenuation is also affected by grain macrostructure, columnar against equiaxed, and by alloy family, which is why the reference base is read by metallurgists and not by a threshold. This is ARTiS working. The crawler clamps to the tube and is driven by 4 metal gear motors totaling 200 watts. Rubber padded shoes carry the transmit-receive probes against the tube surface, coupled with demineralized water. Infrared sensors read the outer diameter as it travels. Gyroscopic sensors record angle, which post-processing turns into a quantified bowing figure rather than an eyeball estimate. It descends the tube and returns, logging a reading every 100 millimeters over the full radiant length. Fixing time is about 3 minutes per tube, so a crew moves down a row quickly. Words only carry this so far. So watch the machine work. What follows is 1 minute of field footage on a live reformer tube. The crawler clamps at platform level. The probe shoes seat against the tube and it climbs under its own drive, while the coolant feed keeps the ultrasonic contact wet. Every 100 millimeters, it logs an attenuation reading, a diameter and an angle. Nobody is on scaffolding. Nobody is holding a probe at 15 meters. And the record is continuous rather than a handful of spot checks. To 190 millimeters. Scanning speed is 2 to 5 minutes per 10 meters and is adjustable. Fixing time is 3 minutes per tube and climbing height is up to 15,000 millimeters. The ultrasonic probe is 25 millimeters diameter at 1 megahertz in transmit-receive configuration with a range of 30 to 100 decibels at 0.1 decibel resolution. Couplant consumption is 500 milliliters of demineralized water per 10 liters. The commercial case is straightforward. 100 tubes take 4 to 5 days by manual scanning once scaffolding is included. ARTiS does the same 100 tubes in 2 days with no scaffolding at all. Manual results are reported in 6-foot segments, which averages away a local hot band. ARTiS reports at 100 mm resolution. Manual outer diameter is 1 or 2 spot readings per tube. ARTiS reads every 100 mm, so creep strain becomes a profile along the tube. And bowing moves from an estimate by eye to a measured number in millimeters. This is the chain that turns readings into a decision. Measured outer diameter and wall thickness give creep strain per tube against nominal dimensions. Creep strain and the Larson-Miller parameter give effective tube metal temperature, the single temperature that would have produced the damage present today. Effective temperature and hoop stress at design pressure give accumulated creep damage. Under API 5791 and ASME FFS-1, a damage fraction below 0.25 passes at level 1. Where it does not, ARTiS carries the assessment to level 3. Retirement is set at a life fraction of 0.8 because beyond that, the damage rate turns exponential. The output is a class per tube, and each class carries an action. Class 1 is as cast sound material. Continue in service. Class 2, creep voids at the inner wall. About 40% of life consumed. Continue and reassess at the next inspection. Class 3, align voids and cracking from inner to mid wall. About 55%. Increase monitoring. Class 4, creep cracking from mid wall to outer wall. About 75%. Plan replacement now, because tube lead times are long. Class 5, macro cracking through 75% or more of the wall. Replace immediately. On site, the scope is 9 items. Expert visual inspection by a metallurgist. Outer diameter along the full tube. Bowing. Ultrasonic attenuation. In-situ metallography by surface replication. Hardness at each metallography location. And at platform level, manual wall thickness, manual outer diameter and magnetic permeability on every tube. Permeability being the indicator for internal carburization. What you receive is a level 3 assessment to API 5791 and ASME FFS-1 Part 10, ending in the date each tube crosses the zero point 0.8 life fraction and its remaining life tube by tube. ARTiS is deployed wherever a primary or autothermal reformer runs. 5 kinds of plant account for almost all of it. Refineries running hydrogen units, petrochemical complexes with steam and autothermal reformers, ammonia and fertilizer plants with primary reformer catalyst tubes, methanol and merchant hydrogen producers, and industrial gas companies with on-site generation. The tube materials assessed span HP modified microalloyed grades G4852 micro, KHR35CT, HP39W, IN519, HK40, and proprietary alloys. That range matters because attenuation behavior differs between alloy families. Two things stand behind every number in this tech. The first is field volume. TCR has been testing materials since 1973, has completed more than 100 reformer tube assignments for Indian and overseas clients, more than 80 of them using ARTiS, and has scanned over 50,000 tubes. Judgments are read against a reference base of more than 100,000 in-situ replica microstructures by in-house metallurgists. The second is the published record. The method was set out by Haribhakti and Upadhyaya in World Fertilizer in the January-February 2019 issue. If you own a hydrogen, ammonia or methanol reformer and your next turnaround is being planned, the useful time to talk to us is now. Not during the shutdown, because tube procurement lead time is the real constraint. Write to sales@tkreng.com or visit tkreng.com. Our work rests on 3 commitments: transparency, competence, and reliability.